Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk about predicates and quantifiers. So here we allow free variables to appear in propositions. For example, let's suppose that p of x is bigger than 3. So we allow a variable x to be fed into a proposition, and that the truth of the proposition is then determined by the value of x. As an example, p of 1 is false because 1 is not greater than 3. But p of 4 is true because 4 is greater than 3. So a predicate is a proposition having a truth value that depends on the value of a free variable. And of course our notation will be p of x. The proposition will be a function of whatever the value of x is that you plug into this particular proposition. It could depend upon more than one free variable. You could have several free variables, for example. An example of this latter case is, suppose p of xy it means x is greater than y plus 1. So the value of the proposition will depend upon both x and y. So if I say 3, 1, that's true because 3 is bigger than 1 plus 1, which is 2. But if I write p of 2, 1, that's false because 2 is not greater than 1 plus 1, which is 2. 2 can't be greater than itself. And so the value of the truth of the proposition will be dependent upon both values. The logic that we develop with predicates is sometimes called predicate logic or sometimes predicate calculus. So we now introduce quantifiers. The first and one of the main quantifiers is for all. So if I write for all x, p of x, I'm saying for all x in the domain that I'm considering for this predicate, p of x is true. You can see that this symbol is an upside down capital A, which stands for the word all. That's as opposed to the following quantifier, which is there exists and so if I say there exists x such that p of x, I'm saying there exists x in the domain so that p of x is true. I'm not saying it's true everywhere. I'm saying that there's at least one place where it is true. There could be more than one. Could be all places for all we know, but at least there is one. For all is the universal quantifier. It's true everywhere. And the backwards E, there exists, is the existential quantifier. So there exists something. Let me give an example. Let's suppose that we're looking at x plus 3 is greater than x plus 2. For what values of x does this inequality hold? Well, it certainly holds for all real numbers. Complex numbers are a different story because we don't have this symbol for complex numbers necessarily. But surely, for real numbers, this should hold no matter what number you plug in for x, because if you subtract x from both sides, you get 3 is greater than 2. That's always true. So the value of x really doesn't matter. So we can express this as, for all x, x plus 3 is greater than x plus 2. And here we're assuming that x is in the domain of real numbers. If the domain is empty, the empty set, this symbol in mathematics is reserved for the empty set, the set that has no elements. Then such a universal quantification for some predicate is said to be vacuously true. It's true for all elements in the domain, but there are no elements in the domain. But it is true for every element in the domain. There just happen to be no elements in the domain. That's why it's said to be vacuously true. As an example, I could make a proposition: for all men on Mars, they have 3 toes. That would be a pretty strange proposition, but it is true for all men on Mars. There just aren't any men on Mars. And so it would be a vacuously true proposition. Only one counterexample is sufficient to show that some universally quantified proposition is in fact false. All you have to show is that it's not for all. There's one where it doesn't hold. So suppose you have this as your proposition. Then if P of A is false for some A, then the universal quantifier proposition is deemed to be false. One counterexample is enough to show that it's not a rule. Here's an example. Suppose I have the proposition: for all x, the floor function of x divided by 2 is prime. Is this a true proposition? Well, if I can find one number where this is not true, then where this proposition is not true, then I'll know that the universal quantification of that proposition will be untrue as well. So let's let x be 8. Then the floor function of x, 8 divided by 2, the floor function of 4, which is 4. 4 is a composite number since it's 2 times 2, which means it is not prime. And the 3 dots in a triangle formulation is the mathematical way of saying therefore, not prime. We deduce then that the original proposition for all x, the floor function of x divided by 2 is prime, is false. Here's another example. Suppose p of x means x is bigger than 3. And so let's compare for all x, p of x, versus there exists x, p of x. We can show that the first proposition, this universal quantification, is false because p of 0 is false, and therefore the original proposition is also false. However, the existential quantification here is true. All we have to show that there is a value of x for which the proposition is true. P of 4 is true because 4 is bigger than 3. Therefore, this proposition is true. As another example, suppose I have there exists x such that x plus 3 equals x plus 2. As you can see, there's no way this equation can hold for any x, because the equation would have to hold when you subtract x from both sides, which would mean 3 equals 2, which is just false. So this equation is false for all values of x. That means there does not exist an x where x plus 3 equals x plus 2, so this proposition is false. So far we have the universal quantifier, the existential quantifier, and next we're going to have the uniqueness quantifier. The uniqueness quantifier means there is only one. There is at most one x such that p of x. There's a unique x such that p of x is true. This is often done in combination with there exists a unique. This is a little bit different from just the uniqueness by itself. Uniqueness just means there's at most one of these things. But when I put the existential quantifier in front of it, it means there does exist one, but there's only one. So this means there exists only one. Exists one and only one. We want to discuss quantifiers and finite domains. Let's suppose our domain has only values x1, x2 through xn. So n different values are the only things that are possible. Then for all x, d of x is really equivalent to d of x1 is true and d of x2 is true and then the ellipsis here meaning dot dot dot, all things in between, all the way down to d of xn is true. So they're all true. Whereas there exists x such that d of x means d of x1 is true or d of x2 is true or all the way down to d of xn is true. So at least one of those will be true, and that makes the whole thing true. Sometimes, instead of writing a big expression like this, we'll write it like this. A big and, where let's say I goes from 1 to n, of the proposition, these are propositions on this domain, p of xi. So we have when I is equal to 1, p of xi, and what happens when I is 2, and this is the starting position, and this is the ending position for this group of ands. For the existential quantification, that'll be a bunch of ors. We often express the domain restrictions along with the quantifier. So for instance, if I want to say for all x greater than 0, some predicate is true, I'll state that domain restriction right there along with the quantifier. How about there exists x in the set of natural numbers such that p of x. So I'm restricting my domain here to the set of natural numbers. What's the order of operations? What's the precedence of these different quantifiers, existential quantifiers, universal quantifiers, etc.? Well, we're going to say that for all and there exists together have the highest precedence, but for all and there exist have equal precedence read from left to right. Equal to between each other, higher than other logical operations. So we read them left to right. So if I write, for all x, there exists y such that x is greater than y, then this would be read in just that way. For all x, there will exist a y, so the precedence is for all first and then there exists. That's a little bit different from there exists y such that for all x, x is greater than y. Notice that this proposition is true. For any x, you can always find something smaller. But there is no particular y, so that every other real number is bigger than that y. So this would be false, where this proposition would be true. The order in which you write the quantifiers makes a difference on the truth of the proposition. A variable x is called bound if it appears in an expression involving either for all x or there exists x. Otherwise, the variable is free. So note, a propositional function, p of x, is not a proposition unless its variables are either bound or set equal to some set particular value. So While P of x won't be a proposition, P of 3 would be a proposition. It's either true or false. But if I write for all x, P of x, that would be a proposition. I'm saying it's going to be true for all x. So these are propositions. P of x is not a proposition. If you have a variable that doesn't have some quantification applied to it, then you don't really have a proposition at all. The statement won't necessarily take only the truth values, true or false. Two statements, P and Q, involving predicates and quantifiers are said to be logically equivalent if they have the same truth values. When propositions P and Q are equivalent, we'll write P is equivalent to Q. Let me give you an example. Suppose I have for all x, P of x and Q of x are true. That will be equivalent to saying for all x, P of x is true, and for all x, Q of x is true. Similarly, there exists x such that P of x or Q of x will be logically equivalent to, there exists x such that P of x is true, or there exists x such that Q of x is true. To show equivalence, we must show that if P is true, then Q is true, and if Q is true, then P is true. So to show that P is equivalent to Q, it's equivalent to saying P with the biconditional P if and only if Q. That gives you this direction and this direction that must be proved. You have to prove the implication in both directions. So for example, let's show that for all x, P of x and Q of x is equivalent to for all x, P of x, and for all x, Q of x. So here's our proof. First, we'll suppose for all x, both P of x and Q of x are true. Then for all x, P of x is true because P of x and Q of x are true, so just P of x by itself is true. But we also have for all x, Q of x is true. And this is an AND statement. So for all x, P of x, and for all x, Q of x. So that's the end of the proof in this direction. To prove this in the other way, we'll suppose for all x, proposition P of x is true, and for all x, Q of x is true. Then P of A and Q of B is true for any A and B. So why not just set them to be equal to each other? Implies P of A and Q of A is true for any A. And that would be just this statement here. For any x, P of x and Q of x is true. How do you negate quantifiers? What if we say it is not true that for all of x, P of x? You're saying this doesn't, the proposition P of x doesn't hold true for all x, which means that there does exist some x for which P of x is false. In other words, there exists x such that it is not true that P of x is true. So we can pass the negation through the universal quantifier, but it converts it into an existential quantifier. What about it is not true that there exists x such that P of x is true? There doesn't exist any such thing. That means no matter what you plug in, P of x is false. In other words, for all x, P of x is false. So negation passes through your existential quantifier, but it converts the existential to the universal. Here's an example. Let's suppose it is not true that for all x, x squared is greater than x. That will be, there exists x such that x squared is less than or equal to x. And you can see that this would be a true proposition. There does exist an x so that x squared is less than or equal to x. In particular, set x equal to 1. 1 is less than or equal to 1. So exhibiting that one element shows existence. This statement will be logically equivalent to it is not true for all x, x squared is greater than x. We can prove that without the negation here, this part would be false because all we have to do is plug in something like x equal to 1/2. 1/2 is 1/4, and that's smaller than x, smaller than 1/2, not bigger than 1/2. And so without the negation, this quantified proposition here is false. With the negation, it ends up being true. What about it is not true that there exists an x in the set of natural numbers such that x squared equals 2? That would correspond to, for all x in the natural numbers, x squared is not 2. Note that the natural numbers are 1, 2, and so on. 1 squared is not 2, and 2 squared is not 2, and anything bigger, 3 squared, that's going to be bigger than 2. So no matter what you plug in, you're never going to get 2. That's because the square root of 2 is not a natural number. So it's not an element of the set of natural numbers. So it is true that for all x in the set of natural numbers, x squared does not equal 2. On this next example, I want to show that the negation of for all x, P of x implies Q of x is equivalent to there exists x such that P of x and not Q of x. So in our proof, I want to recall that P implies Q is equivalent to not P or Q. So we'll start with the not for all x. P of x implies q of x, and rewrite this as not for all x, not p of x or q of x. To pass the not through the universal quantifier, we convert that into an existential quantifier. So there exists x such that it is not true, so that not p of x or q of x. The not here will distribute, but it'll convert the or into an and not is the same as p of x. We'll have and not q of x. And that will be the end of our proof.